Okay, so now we have our last speaker before the break. This is Professor Mokarram Hossain from Swansea University. And Mokarram, I hope now you are well in Spain because yesterday. Okay, so it's my pleasure to present Mokarram. Actually, I meet Mokarram from how many years? I don't know. We started collaborating online in COVID. So Mokarram is associate professor at Think a Big Institute for Modeling, Data, and Artificial Intelligence at Swansea University. So his interests lie in the broad and interdisciplinary areas of soft polymeric and multifunctional active materials, ranging from material synthesis, experimental studies, and computational modeling. Many works on magneto-active and electro-active. And he has published more than 120 papers in journals on materials, mechanics, and computations. And Mokarram is going to tell us today about recent advances in electroactive materials from different dimensions, actuators, sensors, and especially energy harvesters, right? Yeah. So please.
Yeah. Thanks a lot, Daniel. Yeah. Thanks a lot, Daniel, for the invitations and the introduction. Nice introduction. As Daniel already mentioned, I will talk about the so-called electroactive polymers. So you can understand this is basically polymeric material, very soft material that can be used as actuators, sensors, and energy harvesters. Since already Concepcion and other people already talk about sensors and actuators, I will mainly focus on energy harvesters, and hopefully nobody in this session will cover this area, how we can use soft materials or rubber-like materials to produce energy, the clean and green energy, which is the major issue nowadays, right? So what is electroactive polymers or EAPs? So electroactive polymers is, as I said, polymers, but now you are applying the electric field or electric actuations, and you are getting something, for example, mechanical actuations, right? So this is the video that I produced a couple of years ago, and this is a very transparent, the transparent polymer, and then the black actually the grease, carbon conductive grease, or the so-called electrode, right? So if you paint the polymeric material in the top and bottom, and then if you attach with the electric connections, then basically what you are doing through this electric connection at the top, you can see you are charging positive and negative, and due to the attraction of the opposite charges, you will get the contraction along the thickness and expansion in the longitudinal directions. That means you are applying the electric field or electric voltage, and you are getting the mechanical actuation. So this is the actuator mode. So today I will not concentrate on this, but I will go to another area, that is how we can use this electroactive polymer to generate energy from some ambient motions, for example, the wave, right? And okay, so we have huge wave resources, at least in Europe or UK, surrounded by this wave energy. So how we can use this wave motion to generate energy through the electroactive polymer? The principle is very simple, like the actuator. So the figure 1, you have the polymeric material of the thin sheet, thin membrane. You put the electrode top and bottom, and then due to the wave motions, somehow you can think that wave will force the polymeric material to deform, right? And then if you put some charge, positive and negative, that we call it bias voltage, then you are getting a different type of capacitance. You have the position A and position B. You can see, if you look into the equation of the capacitance, now you have very thin, right, compared to the first case, and you have the large area. That means capacitance is very high. Now, wave disappears, the polymer is largely elastic materials, more or less. It will come back, and then you will get the minimum capacitance, and this difference of the capacitance you can harvest as the energy, right? More or less, this is the cycle. And the next wave will come, and then, so I was lucky. My first PhD student was supported by this company, so I would like to show you a video, and this is a very practical experience. Okay. Hopefully you can see. If not, you will see. No? Okay. Doesn't come? Yes. Okay.
Out to sea, safely beneath the ocean's waves, sits M-Wave.
Okay, so
Bombora's pioneering patented technology.
I cannot. Okay, so here you can see this is the flexible material device that put underwater, and due to the wave, this flexible material, it's a little bit difficult. No. Oh, okay.
On the top. You're on the top. Here. On the right. Good.
No, you have to. No. This. No. Okay. Oh. So you can see. So this is the elastomeric material filled with air, and due to the incoming wave, this will inflate and deflate. And since it is filled with air, and the air will pass in some device that is connected to the generator and motor, and that will create the energy. So here, this is the typical application of the flexible device using the rubber-like material to generate energy. But we said, okay, now we are interested to see, no, now we are not interested to make many parts, for example, the so-called, so this is the device. You have the flexible membrane. So it's called primary mover that separate the water with the main device. And then you have other components and so on. Now, our next target is, okay, can we use this elastomeric material as the generator? So I don't have any generator separately, right? So this polymeric material will be stressable according to the principle that I have shown you, and it will generate the energy. Yes, we can. Let me show you another device. So that is called DAG, dielectric elastomer generator, right? So now the simplicity of this, we don't need extra generator, extra device, and so on. The rubber-like material will be stressable, and that will create the energy. So the problem here, in the previous slide, you can see that it is the stressing and de-stressing, right? And how many cycles it will survive? That's the main question. Maybe millions, couple of millions. That means after few months or few years, you have to change the device, right? So the fatigue issue is the major issue for this rubber-like material as a generator. So people say, okay, now can we think about it in a different way? So instead of this thin sheet, can we replace the material and put as a dielectric liquid, right? So this is very recent development. And then you can see now we have this very simple device. Now we have the electrode in the top and bottom that is filled by a fluid. And a fluid is basically has unlimited number of cycles. So you can go and fluid will come back and you can continue. So there is no dielectric breakdown compared to the elastomeric material. And then you can consider the self-healing material or self-healing layer, right? And the principle is the same. You have the electrode in top and bottom, and then that could be flexible electrode or that could be rigid electrode. Rigid electrode means you have like this, and you can deform. You don't need to deform the electrode. Just change the volume, and that will change the capacitance. So, and that is called dielectric fluid generator. So now we have two types of generator, dielectric elastomeric generator and dielectric fluid generator. But for the both case, the fatigue is a major issue. So either you will covered by the electrode or elastomeric layer in the top and bottom, and these materials are fatigue prone. So next slide, I will concentrate mainly on the fatigue issue. But before that, we can also make this flexible material as a small device. So let's say a small generator, and then we can connect to make it large generator. So that means this is a part of the so-called metamaterial community, right? So either you can use as a dielectric fluid generator, or dielectric elastomer generator, and you can make a big, so this is hexagonal device, and you can make it as a dielectric elastomer. You can paint the top layer and bottom layer, and due to the wave, it will stressable and come back, and that will generate the energy. So, and then this small device, you can connect to make a big device, and so on. So how it looks, so in the top, you can see the principle. Either it will be stressable or just flexible. That will change the capacitance. And then the small components, that could be several micron, several hundred micron, right? Or several centimeter. And then you assemble, and that could be a big system of generating energy. So this is the recent development. I was lucky I was working with a company that was funding a PhD student in this area. So another area is the flexible sensor. I think you already, Concepcion, talk a lot, so I will not go into details. But here, one of the major questions that she has shown, like this, right? So how your sensor will act when you have millions of cycles, right? Does it survive, or the prediction is accurate during the cycle, right? So my main focus is to understand the capacitance or the resistive behavior in millions of cycles. So if you want to use this flexible sensor in dynamical case, then you need to understand that up to millions of cycles, my sensor works as it is, right? It can predict as the virgin case. So, okay, so let me show you one sensor that one of our PhD students just prepared. And here, this is the sensor. I think Jesus and Rogelio have recently seen. Then you can see, if you deform it, and you can see the capacitance and resistivity changing. So this is the work of one student, but my another student is doing how to design this conductive path, right? So you can create different metamaterials and so on. So, and then you can put the top layer and bottom layer, and you can just, she joined recently. This is the earliest course. But my main target is to see how your sensor is more or less insensitive with the cycle, right? Either it could be resistive sensor or conductive sensor, but I want to see that this sensor property does not vary over time, over cycle. Okay, so I'm not going into details. Let me go to the area that is very, very important for the company. How many years, how many cycles this cell or metamaterial or the DAG or DFG or the flexible sensor will survive, right? So if you look into the applications, it's not only about the energy harvester. It's not only about in flexible sensor, skin mounted sensors for the training and sport purpose, right? So you have millions of cycles. But interesting thing is, you cannot provide the data with the uniaxial fatigue. You said, oh, I take a dog bone sample and go to the machine, instrument machine, I do this. No, it will not work. Because you are working at least in a membrane type shape, and you are getting multi-axial deformation. So I was lucky to get some funding a couple of years ago to develop a customized system that can do multi-axial fatigue test. And this is the machine. You can see this is really, really customized machine for submaterial. And this is the machine. And you can put the sample underwater. So this is the DIC underwater. So you can track the deformation underwater. And the water temperature you can change if you want. So we can go up to 60 or 80 degrees centigrade temperature. So we have the recirculating system, and it can keep the temperature constant. But most important thing is you can deform the sample up to 500% deformation, okay? And sensor is very, very sensitive. So we have 5 or 10 Newton to 2 kilonewton load cell. So it's a large range. And you can test biological tissue or hydrogel and so on. And we have different type of waveforms, so square, triangle, sawtooth, and so on, and sinusoidal. So you can use different type of frequency and the waveform as well during your fatigue test. So this is the close look. This is the biaxial sample, the cruciform sample. with the DIC, and you can see underwater. Okay, so the same machine, if somebody said, okay, I'm interested to see only uniaxial data underwater. Okay, fine, I can do that. So I will just deactivate the other axis. So both axes are completely independent. There is no connection of axis X with axis Y. Okay, so you can do, for example, 3 dog bone sample at a time underwater without water. Or then we modify. So, okay, if only 3 and that takes 9 months, no way. So what we do, we said, okay, we change the system. Now we can test up to 24 samples, and 12 samples in one axis and 12 samples in another axis, right? And then you can do the averaging very quickly. And then on the top we have the DIC, and the DIC can monitor when and at what time, which cycle, and what sample breaks. So we are done with uniaxial, very good. So far, so good. Then I got another funding, so they said, can you enhance the fatigue life? Okay, and what are the ways? There are plenty of discussion in the literature. If we incorporate some so-called 1D material like carbon nanotube or 2D material like graphene, then people say the fatigue life will increase. But we found it's a stupid innovation because what people did, people cut the sample and they do the fatigue test, and they found that this crack does not propagate because there is some barrier. Fine, but what is happening if you take a virgin sample and do the fatigue? I will show you. Okay, so before that, we prepared the sample in our lab by 2 ways. So we mix the CNT or carbon black or other pillar in the liquid phase and the solid phase, right? Liquid phase means we dissolve the, for example, natural rubber or other polymer and put the filler, and in the solid case, we have the powder and mix up with the gum, and that makes the so-called dry mixing, okay? And then we see what is happening. So this is the uniaxial fatigue, and we see due to the incorporation of the CNT, there are plenty of cracks at the beginning. And these people do not consider the virgin sample. They took some sample and they cut the sample. So that means you can say that the crack propagation approach and then the so-called other approach, crack initiation approach, is the same. It will give you the same fatigue life for unfilled polymer, but not for filled polymer. Okay? So we found that for CNT-filled elastomer, the fatigue life is significantly less if you take with the virgin sample. So here you can see. So we did 2 types of fatigue test. One is the submerged. So we put the sample under water, and we did this fatigue test with the virgin sample. That means it took 6 months to get 1 set of data, right? And you see that, or 3 months, 6 months sometimes, and you see for the dry case, the dry means I'm pulling it up to 100% in dry condition, no water, and I'm putting this sample up to 100% in wet environment. That means with water, right? And I found that the submerged condition fatigue is much more high than the dry condition. Please keep in mind, this is not of the synthesis. I do 2 types of synthesis. One is dry and one is wet. I'm not talking about the synthesis technique. I'm talking about the testing condition. One is dry, one is wet. If it's wet, then you are getting higher fatigue life. That means if you do the fatigue in the sea, you will get higher fatigue. The reason is, during the fatigue life cycle, there is significant amount of heat generation, okay, in dry case, and that decreases the fatigue life, which is not the case when your sample is underwater. And what is happening? If you take the sample that is produced from dry synthesis technique or wet synthesis technique, and you see, okay, for dry, you get the higher fatigue life, and the wet, you are getting lower fatigue life. The reason is, okay, so reason is, then we did some microscopic analysis, and we found that during the synthesis with the dry condition, when you're mixing with the liquid, there is significant amount of bubbles formation inside the sample. And that makes the fatigue life really, really less compared to the dry condition. Okay, so this is, the left side is the dry condition, and the right side is the wet condition. So you can see there are some big bubbles. And when you test the sample with, test the fatigue test with a virgin sample, there are immediate cracks due to these big bubbles. Okay, so we are happy with the work that we did with the uniaxial fatigue with different synthesis technique, dry fatigue, wet fatigue, and so on. But please keep in mind, why you are interested to do in this? Because of this web company, they said, oh, we don't know anything about the fatigue life. Can you do the test? Before taking this device or the technique to the next level, please give us some fatigue data. Okay, and this is the same thing for the flexible sensor if you want to put in the dynamic condition, right? So you need to see whether the resistivity or conductivity is varying over the cycle. So, okay, we also did some biaxial. Now I'm moving to biaxial test. Biaxial, so here, this is the cruciform sample underwater. And it took a lot of time to understand the speckle pattern and the DIC underwater. And you can see, we can nicely track the contour, the deformation contour underwater. Or if you, if you could take the square sample, it can also nicely track the speckle pattern underwater. So this is not dynamic test. This is not about cyclic test, okay? Then I said, okay, let's do some biaxial fatigue test. Please keep in mind, this is biaxial means biaxial. It's not you have the inflation bubble, no. I'm not doing, because there is axisymmetric equibiaxial, right? We're interested to do non-equibiaxial. That means you can apply the force in x-axis one type and y-axis completely another type, right? This is the case if you look into the wave device that I have shown you. It's a non-equibiaxial. So this is at first we did the equibiaxial to see where the crack form, right? And when I was talking to different people about the biaxial fatigue, they say, oh, you can't do because the fatigue will happen in the gripping section, right? And this is the case. So we found the fatigue start or the crack start at the gripping section, the diagonally, either in some of the gripping section. Then one way is to make the gripper, I'm not sure I have this photo or not, but I did not put it here. So then we put some glue, and then we make the S a little bit thicker, but still problem is there. Then we move to the so-called the cruciform sample. And here, what we did, after a lot of trial and error, it took a lot of time to understand that, okay, if we do the S sections a little bit thicker compared to the middle section, because our focus is the middle section, right? And what is happening. So this survives after millions of cycles. But here, what we did, we glue the S section compared to the middle section. But we don't want to glue, because sometimes the glue somehow breaks, right? Then what we did, okay. So there is another approach we found in the literature. People say if you make the sample like this way and you make some longitude or some, I should say, bar type thicker S, then the gripping will be nice. But we do not test. Here we use just thick S's compared to the middle section, and it survives millions of cycles. And then we tried a little bit more, so-called non-equibiaxial. That means we pull the sample 100% in one direction and 10% in another directions. What is happening? So here, so both sides, this side we have 10%, and that side we have 50%, I think. And here, this is not glue sample. It's one sample. So we cast the sample as only one sample, and the middle section is thinner compared to the other section. So now, our DIC will only concentrate on the middle section. And this survives. That means we don't have any failure from the S. If failure happens, it should be in the middle sections. So that works fine. So far, we did, I think, 9 million cycles so far. So this is about biaxial, non-equibiaxial fatigue so far. And again, please keep in mind why I'm concentrating on the non-biequiaxial, because of the application, either in web device or if you have the sensor, skin mounting sensor, or are experiencing non-equiaxial deformation, right? So you cannot take into account only the fatigue life from uniaxial dog bone sample and you can play. No, it's not possible. Okay, so now I will quickly move to actuator, how we can use the electro-active polymer as an actuator. But again, my colleague Rogelio will talk about more about electro-active polymer hopefully tomorrow. But I'm not going into details about modeling of electro-active polymer. I will show you some more results, experimental results of electro-active polymer as actuator. Okay? And think about temperature. Think about Madrid condition and think about Swansea condition, right? In winter and in summer. Swansea is now minus and Madrid is 18. And you are sending a robot to Swansea or to Swansea to Madrid and you're saying, okay, it will function well. No, it will not work. You are worried about viscosity. I'm worried about temperature as well, right? So I was working with a polymer that is called VSB. It's a commercially available polymer for 3M. And I did my postdoc in Germany. And I did the test during summer, and I was writing the paper in winter. And then, I found that I need one data. Then I asked my student worker, I said, can you do more tests? Then he came up with some new results that is completely different than what I said. What? I said, did you test? I mean, this is a very good student. I can rely. But this is not Dr. Hossain. This is the data I produce. Believe me. I said, okay, let's go to the lab together. And then I found that it has more or less double stress than the summer case. That means if you have less temperature, right, or high temperature, it's 5 degrees centigrade temperature, increase the stress response almost double. Right? So you are talking about room temperature. Room temperature in winter and room temperature in summer is not the same, right? Unless you maintain the temperature constantly, right? So 5 degrees centigrade temperature gives me almost double. So what is the novelty here? We published a lot of papers since 2015 in the last 9 years. So what we did, in the left side you can see, now we have a device that can do electromechanical actuations. That means you can deform the sample. You are applying the mechanical force as well as you are applying the electric voltage. That means simultaneously you are applying the electromechanical field. But then we put inside a chamber where you can control the temperature up to 110 or 120. So let me show you the result. So typically this polymeric material is viscoelastic, except 1 or 2% polymeric material. 95%, even someone tell you that I use a hyperelastic model and it's nonsense. None of the polymeric material are hyperelastic. It's viscoelastic, 99% or 95% at least. So that means it is a dependency, it has relaxation and so on. So you can see the polymer that we have been using, the VSB, is a commercial polymer. And then you see rate sensitivity, right? Or different strain rate, and you are getting. And then if you do the relaxation test, it has significant amount of relaxation if you pull the sample and you wait for a couple of minutes, and then you will find the relaxed state. Okay, so this is about mechanical test. Then what will happen if you do electromechanical test, right? Electromechanical test means you are pulling the sample, at the same time you are applying the electric voltage. Since you are applying the electric voltage along the thickness direction, the polymer will expand in this direction. So in the same direction you are applying the mechanical field. That means you are getting a less response compared to the mechanical case. So this is the case. So if you increase, this is the temperature. I'm sorry. This is only a fixed strain rate, but with temperature. Look at here. So you are getting a temperature, I cannot remember, it's 20 degrees centigrade temperature. This is 0.8. And then when you have 40 degrees centigrade temperature, it's almost double, right? 0.8 to 0.36. That means the temperature increase, you are getting less force or less stress. So what is happening? The same thing if you apply the temperature during your relaxation test, and you are getting the less response if you increase the temperature, and so on. And so from there, you can extract the so-called equilibrium stress, and then you can plot. Then you can clearly see that the temperature has a significant influence on your viscous response as well as your hyperelastic response or equilibrium response, both. And then in the same chamber, we apply the electric field. And in the left side, you can see, as I mentioned already, that if you have the deformation in the longitudinal direction and you apply the electric voltage in the thickness directions, that means you are releasing the force. And that force you can clearly see in the top. That means if you have a 0, that means no electrical force. And if you increase the electrical force or higher voltage, then you will get a reduced deformation because you are releasing the force in the perpendicular directions. So, and then finally, we combine mechanical, temperature, and electric voltage, and this is the experimental data. Good news is I also did modeling of this, but I don't want to present here because my time is out. Thanks a lot. Okay.
Okay, thank you very much, Mokarram. Okay, questions?
Yes.
Yeah.
Thank you. Thank you, Mokarram. It's really super interesting presentation. I have a couple of questions for you. The first one, maybe the easiest, the DIC. I use DIC for the soft material, submersion water. I was really impressed to see the full strain stress field. And I don't know what speckle did you use for the soft material because it's a challenge.
Yes.
And I'm not sure if you do fatigue tests. I assume you didn't do that for DIC.
So
right?
far, for all the tests with the DIC and a speckle pattern, we did only for
what did you
couple
use?
of cycle, not fatigue cycle.
Yeah.
So the speckle pattern, very good question. That means you failed, right? And we are successful. That's thanks a lot. Oh, sorry, not to undermine. That means you know there is a challenge. Okay. Oh, can you please? No, I cannot show here. So I want to. Yes. So here, actually, if you see, the quality is quite good, right? I have more data where we did the crack propagation up to 200%, and the company is so impressed, they said, okay, we want to extend your contract. So the reason is we did the so-called more regular pattern, so the brush, and then we spray. So we combine both.
Because when you move it, the mechanical properties of speckles change.
Yes, significantly.
And you
Yes.
need to track
Yeah,
correctly.
so that means the way is we combine both approaches. The speckle we paint, right? And then we brush.
And how you protect it from the water?
Oh, this more or less, it is, we try with different coating system, and one coating system survives. It does not disappear with water. Yes.
Okay.
There are
Interesting.
something commercially available.
Okay.
You need to play with.
The second question I find it's interesting about the fatigue when you design this structure. I think if you go slide 17, I'm not sure if it's 17 or 16. The one with the shoe, the Adidas 4D shoe and...
Motivation, you mean?
No, the Adidas 4D. Yes, this one. Yes. Yeah. So this is a very interesting one, but because the one that with the white and red, this using two different material to increase toughness and delay damage. And I think this is completely different what you have been doing.
Okay, so here I want to...
I still didn't ask a question. Maybe I have to continue my question, sir.
Yes, please.
So the trick is that from your work, I understand there's two different techniques you can achieve the fatigue material structure that has fatigue resistant. So here, this is two different materials, soft and hard, and that's what happens in nature. Like some animals, you have soft and hard, and you play with geometry to increase toughness and delay damage.
Yes.
So it's different between what you show and this image. Yeah.
Okay, so here, actually, I want to motivate you why I'm interested to do the biaxial fatigue or non-equibiaxial fatigue.
Yeah.
Because for this approach, the paper that Suo group and other people are doing, you are taking and we are pulling in one direction, but you don't know there is a change in the other direction. So that means you are giving me data, taking the stressability in one direction, but you have entanglement in the crosslink in other direction. I don't completely forget. And you don't consider the influence in other direction. So I'm giving you the motivation why I'm interested to do biaxial fatigue. The reason is this. So we have the crosslink, and then you have to take into account, especially if you want to increase the fatigue life through this design. My approach is not to design. I'm taking from market. I'm talking from literature. But my approach is why
But I'm interested in your opinion about that, because what you mentioned next slide, it's not exactly the same approach. You're talking in more the material level, here in more macroscopic level. So they use soft and hard material. Do you see that there's differences if you want to design a structure that can delay damage, and we don't use self-healing?
Yes,
If we
we
have
are doing
structure.
Yes, we are doing right now. So again, I'm not designing new synthesis. I'm taking. I believe that what SWO group did, fine, but I want to test what is happening with the biaxial fitting.
Very thanks for the presentation. It was really amazing. Seems like a animal briefing or something like that. I think it's a really big project. I was thinking using, maybe if you are thinking to miniaturize the system in order to, how to say, use for drones underwater and, how to say, improve the autonomy of some kind of robotic things, because I don't know if it can be used in small devices. Yeah,
the autonomous, that means whether we can use as a sensor and the energy harvester simultaneously, for example, right? Yeah, so that I do not do in that direction, so to be honest with you. So here, I'm just focusing how the soft device or the architecture can give me some energy. But you were right, we can make more autonomous, and this is one of the reason the company that I have shown you, they want to make this flexible device as a self-sensing as well. So that can give you the crack propagations because they're underwater and you don't have any the monitoring mechanism, right? So if you develop some sensing mechanism and that can give the warning, oh, your flexible device is about to fail, so hey, please do something. So yeah, of course, this is one. And then as well as we can use as an actuator. So this is the area in future we need to focus. The same thing we can use actuator, sensor, and energy harvester. Why not? Yes, we are moving in that direction.
Okay, any other question? Okay, here Fabrizio. Maybe in the meantime, a quick question. So you saw that under Virgin conditions, with the conductive particles, they behave much worse, right? So my question is, did you optimize a vacuum system to extract the bubbles and also coating to get? So do you think this is something that's going to happen just because of the sharp, contrast in stiffness, or this is more about the adhesion that you can get from the...
Very good question. Thanks a lot, Daniel. So two things. One is, if I want to make this as a sensor, then we found that the weight technique is better. Because then you can disperse the CNT nicely. And then when you stress it, you will have the channeling very easily compared to the weakly dispersed. So what is your application? If you said, okay, I want to make sensor, and in that case, fatigue life is maybe not my first priority. My first priority is the high sensitivity, right? So in that case, I would prefer to go with the weight method. But if you want to make as a device for energy harvester, what the company is struggling to make is a large-scale device. The large-scale membrane is, for example, 6 meter by 6 meter, right? And in that case, this weight method is not the ideal for them. They have a huge amount of material, and then they throw the powder, and they mix it, and make the sheet. So in that case, they want to say, okay, can you tell us what is the fatigue life if you go on weight method and dry method? Then you said, okay, dry method, what you are doing is fine. But it depends on application.
Okay, really good point. Fabrizio?
Mokarram, really fascinating talk. I have two questions, but probably I will ask one because the other one next time. But just quick, regarding really the natural rubber and the carbon nanotubes, just to clarify the manufacturing process, did you first really made the compounding with the screwdriver and then?
Yes.
Okay.
Yes, we did, yes. Yeah,
Okay,
the professional way, we did in TARC in Huddersfield. I mean, they have the best facility in the world.
Okay, so you have the time for the second question in that case. obviously, I was very interested on your cellular device, and I find also very interesting also the type of work that you try really to architect really the sort of the conductive circuit.
Yes, that's my student just started. She said, I want to say, okay, go ahead, whatever you like.
You did well. So I just have a question. In the sort of design of the single, if you want, units that you showed before, you see that in essence, every unit has got really inlet outlets in order really to control the fluid.
Yes.
Okay. In the demonstrator that you show, you have really several cells, and so there is a relatively size-scale effect when you inject effectively the liquid there in time. Is your intention really to look at more size-scale effects when you increase the number of cells, or do you want really to keep that kind of scale?
Okay, so I cannot go into details because of the IP confidentiality. I'm working with the companies. What they're doing, up to now, they have 120 different design. And they set up a matrix. If it passes this, then it's a good cell. Okay, so at first is the design. So they play with, I show you 4 design, taking from them, okay? But there are a lot of design options, but they have a criteria matrix. If it passes all the 5 criteria, they said it's a best design. And then scaling effect, yes, we are not in that direction yet. Right now, we are doing 2 things. One is the design. Second thing is I'm trying to analyze the fatigue life. That is the next. And the third is we are also playing with the manufacturability to enhance the fatigue life. So these 3 things we are doing right now. But in future, yes, that is one of the area we might look. But up to now, new design and synthesis and fatigue life.
Thank you.
Okay, so thank you very much again, Mokarram, and I will ask thanks for the 3 speakers. So thank you all.